Solving trig equations using identities. So take a look at the example problem we have here. It looks kind of quadratic, and that reminds me of a method we've learned earlier, the factoring method, where I get a 0 on one side and I factor the left side. The problem with this equation, though, is it has two different trig functions in it. There's a sine and a cosine. Well, sometimes in those situations, you can use an identity to help you rewrite the equation so that you can use that factoring method. What you're supposed to think of when you see sine squared is, well, wait a minute, I can always replace sine squared with something involving cosine because of the Pythagorean identity. In fact, sine squared x is simply equal to 1 minus cosine squared x. We've used that identity several times in that way. And by making that replacement, using that identity, I've now turned this equation into one that only involves the cosine function. Let's go ahead and clean it up and see what we've got. So I'll distribute here. And then I notice that I've got this 2 on both sides that I can easily subtract out. And now I'm left with negative 2 cosine squared x plus cosine x equals 0. Well, this is much better looking than we had at the start. I do have the 0 on the right side, which is great. I only have the cosine function on the left, which means I should be able to now use that factoring method to accomplish step A. The factoring is actually pretty simple because I have a GCF. I have cosine x that's common to both of these, and so I can pull that out to the front. Actually, I think I'll go ahead and pull that negative out as well, leaving me with positive 2 cosine x here. The sign would change in the middle, and just a 1. I pulled out the whole cosine x. Let's check. Negative cosine x times negative 1, yes, would get me back to plus cosine x. Then I can use that zero product principle. Obviously, one or the other of these two factors is equal to 0. So either it's the negative cosine x or it's the longer one. We can now get that cosine x by itself. Here I'll just have to divide by negative 1. Cosine x equals 0. On the other one, I'll have to add 1 and then divide by 2. And I end up with cosine x equals 1/2. Everything we've done so far has been to accomplish step A. I used an identity so that I only have one trig function. Then I used the factoring method. And finally, I actually now have two simpler equations that fit the step A pattern. I'm going to have to now solve each of these two equations, put my answers together, and those will become the solutions to the equation. Let's start with cosine x equals 0. When I see 0, I know I'm going to be drawing a unit circle picture. Let's see, the cosine is the A coordinate. Where would I have that? I'd have that here at the point 0, 1. I'd also have that down here, 0, negative 1. Those are the only two spots where you get an A coordinate of 0. So we're talking about this angle and this angle. We are working in degrees in this problem. Well, those two angles obviously are 90 degrees and 270 degrees. Let's start making a list over here. Those would be the only two solutions within one period. Then we'll go to the other equation, cosine x equals 1/2. Let's see, cosine is only positive in the first quadrant and then in the fourth quadrant. All students take calculus, fourth quadrant. So I will have a first quadrant angle and a fourth quadrant angle. Let's draw in the reference triangles. Cosine is adjacent over hypotenuse. This is one of our special triangles. I'm not surprised because I'm finding exact answers. This is just the 30, 60, 90 triangle. This would be a reference angle of 60 degrees in each case. 60 degrees opposite the root 3. So the angles we're talking about would be this first quadrant angle and then this fourth quadrant angle. Well, the first quadrant angle is pretty obvious. It would just be 60 degrees, so that's another solution we can add to our collection. And then how about that larger red angle there? Looks like it comes 60 degrees short of going all the way around, so that would obviously be 300 degrees. Well, do I need to continue on to step C now? I don't. I only wanted solutions within 0 to 360. We just found them all. We didn't use substitution in this problem, so we don't have to carry out step C. We're finished. Here are the 4 solutions to this equation in the requested interval. Thanks for watching.